Greetings to the respected sir. My name is O. Joshna. Here I am giving the presentation on balanced energy regularization laws for out of distribution detection. Here we can improve the ODD detection with BRL, and my teammate is Abhinav Pandey. Before moving further, we will look towards the content. Here we will see first introduction and the OOD detection and OOD detection in image classification and in a semantic segmentation and leveraging auxiliary data in OOD detection, energy-based out-of-distribution detection, and proposed methods and training procedures, results, outcomes, conclusion, and references. Coming to the introduction of the presentation, here we will talk about the balanced energy regularization laws. Balanced energy regularization laws is nothing but it is a technique that used in out-of-distribution detection tasks, particularly in deep learning models. It is designed to address the class imbalance problem arises in OOD detection. Class imbalance problem means it refers to a scenario in machine learning where the classes in the training datasets are not represented equally. In other words, we can say that there is a significant difference in the number of samples belonging to each class. This imbalance can cause challenges during model training and evaluation, particularly for the classifiers. Mainly the balanced energy regulation loss, the technique used in out-of-distribution detection task, particularly in deep learning models. And OD detection is the task of identifying whether the given input falls outside the distribution of the training data. And it is used for the designed to address the class imbalance problems that often arises in OD detection. And what is meant by the OOD? It's out of distribution. That is, for example, if we take the cat, dog, and elephant as images, if we will train them and we'll get the output as respective of the image. And if we test with the new data like with frog, and it will go to the network and it will go under the network regressions type models, and it will detect like which similarity is higher. It will detect by the model, so it can comes under the out of distribution. So we can say I do here out of distribution detection is nothing but identifying the inputs outside the training data distribution, and it is a crucial for model reliability in safety critical applications, and also class imbalance fewer OOD samples than in the distribution ID samples. And coming to the OOD detection in image classification is nothing but the definition for that is out of distribution detection in image classifier classification. There are two approach methods. One is uncertainty estimation and architectural loss modifications. Here the objective is to enhance the model performance and robustness. Here from the figure we can say these are the discriminators. Here we are having three data sets which are having different samples, and this is the decision boundary. This is the density estimators. Here we have the decision with the decision boundary. We divide the things into two parts, and here these the things are the out of distribution samples. And OD detection semantic segmentation is nothing but it is the detection challenges in semantic segmentation, and the benchmarks for that one is evaluation criteria like the image classification, and it is evaluated by the pixel by pixel representation, and it is having many enhancing methods like MSP, entropy, and Mahalanobis energy, Max Logit, SML, Bayesian Deep Lab, image resynthesis, and SyncBoost. And the other one is leveraging auxiliary data in OOD detection. Leveraging auxiliary data in OD detection is nothing but using extra information or data sets together with the primary training data to improve a model's ability to detect and handle samples that are outside its usual distribution or significantly different from what it was trained on. That is, here there are methods for that is to utilizing the auxiliary data for improved OD detection. There are techniques like cut pasting object masks using raw pixels from auxiliary datasets. And the datasets here we are using is ImageNet and AD20K and Coco. Then examples are like MetaOD, Pebble, Dense, Hybrid, Binary Classifier based approaches. And now my teammate will tell the thing.
Greetings to respected sir. For proposing, my name is Abhinav Pandey. Here I will explain the further part of our presentation. Before saying anything, we will speak towards the proposing method. For proposing the method, our objective is to balancing energy regulation laws for improve OD detection. We formalize it by discrimination neural uh, classifier and softmax probability vector f of x. We'll approach it through outlier exposure and energy loss, energy based OD detection outlier exposure. And first I will see outlier exposure. Outlier exposure is nothing that it is simply means that we will use the data which is already available, means already trained with the help of already trained data we will regularize the OD and data. Uh, that means we use the already available cross entropy loss for in distribution data and regulation loss for OD in data. We minimize the cross entropy loss and outlier exposure regularization. The components in this outlier exposure are cross entropy loss for ID data and energy regulation loss for OD data. Uh, Now we'll see balanced energy regulation loss. What is this? This is simply the property of the OD sample is modeled in the new term Z, which measure whether a sample belongs to a majority class or a minority class. The main idea of our loss is to use a larger regularization to OD samples of majority class compared to OD samples of minority class. This all in balanced energy regulation loss. Now we'll see the conditions for balanced energy regulation laws. This is z-term calculation. That means in z-term we define a parameter z. In this we will estimate prior probability distribution for OD distribution. And then we will see posterior probability in which we computing softmax at the output of a discriminative neural classifier, which we already defined as f of x. Now we'll see generalized prior probability. With the in this generalized probability, we modeled our scenario with the help of a hyperparameter gamma. The generalized version of our model is defined using Z gamma, which incorporates gamma for prior probability differences. The loss function is simply the balanced energy, L energy balance comprising square hinge losses for in distribution and adaptive loss for OD data. Hinge loss is the loss function used for training classifier. The hinge loss is used for maximum margin classification. Mostly it is used for SVMs, that means support vector machines. And adaptive loss are margin and weight components adjusted based on Z gamma. Now we will see that energy based out of distribution detection. Uh, Previously we see outlier experience outlier energy, and now we'll see energy based OD detection. What this will approach through cross entropy loss for in distribution data and energy regulation loss for OOD data. For energy regulation loss, we define different outlier explorer and also define square hinge losses for energy. The components for our energy-based OOD detection distribution, that square hinge losses for both in distribution as well as out of distribution. Yeah, there's a one graph which is explaining OOD. This X is our input data, and we will applying CNN method for classification, and then we will get energy function. Here is the graph which shows the frequency. The frequency is nothing but the maximum softness probability in things, and with the energy. Here there is a threshold between out of distribution and in distribution. Here we see that the for out of distribution that probability frequency is too high as compared to in distribution. Now we will move towards the training procedure. For training processor, we can see that for we are using balance energy regularization, and in this first we'll give input. Input is nothing but our pre-trained model, that is small f, and capital F is our softmax uh, probability function, and the data which we are using d in and d out. D in for distribution training set, and d out is nothing but OOD training set. We will do it in two steps. In first step, we'll do see towards the OOD training set. Here we will compute a prior probability for OOD, and in second step, fine tuning the pre-trained model for in distribution data, and will minimize our uh, hinge hinge loss there here. And what is here, there's one term fine tuning. Fine tuning means when fine tuning a pre-trained model for both MSP and energy score can be influenced by the adjustment of model parameters to better fit the data distribution. This is for in this means fine tuning, and steps inferences on OD data and fine-tuning of pre-trained model. And objective of our this algorithm is minimization of cross entropy loss and balanced energy regulation loss. We can see that the flowchart of our algorithm. We will start by pre-training our model. Then we give input data as our pre-trained model. In step one, we will see inference on OOD data, in which we will compute the prior probability of OOD, and then in step two, we will see fine-tuning of pre-trained model. Here we will see the updated unfrozen classification layer of our minimizing fine-tuning pretend model, and then finally we end our algorithm. Now we will see our results. MSP, we will see that the graphs which is MSP versus energy score with and without fine-tuned on our data set. On our dataset. What is meant by MSP? MSP stands for maximum softmax probability, which measures the confidence of the model prediction for a given input. And with the energy score. Energy score is a metric derived from the energy-based model, which quantifies the likelihood of a sample being in distribution or out of distribution based on its energy value. Here we are using here we have the our results of the graph, which MSP versus energy score, and the model name and our frequency results, and that for softmax square output is 51.04 and our is 33.01%. Softmax with fine tune 8.53 and energy score with ours 3.32%. Now we'll see outcomes of our implementation, that by making inferences based on already trained models, we can explain the imbalance distribution of auxiliary OD data We can also suggest a novel-based energy regulation laws to address the class imbalance in auxiliary or the data, and we can also propose we can also balance loss performance, which is better for audit detection than the previous energy regulation laws. We also sort of performance for audit detection into task is achieved by our audit detection method. Now we'll conclude our presentation that whatever we implement will is we got a little bit means will a little bit tends to the already means our result is already approaches means that error is not that much. We are we tried our in a good level that our softmax and our energy score is having 17% difference of only 17%, which is not as yes, it is much, but not as much. Now we'll see in concluding that our proposed method enhances audit detection through balanced energy regulation, the property modeling of OD sample, adaptive regulation based on class distribution. Also, we improve robustness and performance in OD detection tasks. Now, these are the references which we use for our presentation, and the very thank you.
That's it.